This is our second video on valence bond theory, page 137. Next we're going to look at compounds with trigonal bipyramidal electronic geometry. These would include compounds of the type AB5, central atom and 5 bonded atoms, AB4U, central atom and 4 bonded atoms and 1 unshared pair of electrons, AB3U2, 1 central atom, 3 bonded atoms, 2 unshared pairs of electrons, and AB2U3, central atom, 2 bonded atoms, and 3 unshared pairs of electrons. We'll start with AB5. Now recall that the second period elements cannot accommodate more than 8 electrons in the valence shell because only their 2s and 2p orbitals are available. But also recall that central atoms of the 3rd, 4th, and 5th period can accommodate more than 8 electrons because they can hybridize their ns, np, and their nd orbitals. And so phosphorus can accommodate up to 10, sulfur up to 12, chlorine, bromine, iodine up to 14 valence electrons using their d orbitals. Recall also that in the triangular bipyramidal structure, the unshared pairs of electrons will preferentially occupy the equatorial rather than axial positions because equatorial positions are less crowded to make room for these unshared pairs of electrons that take a little more space. I'm going to suggest we start by drawing the structure of PCl5, phosphorus pentachloride. Phosphorus is in group 5A, so it will have 5 valence electrons, 1 pair and 3 unpaired electrons. And we need 5 chlorines for this compound. The halogens are monovalent often, as in this case. Whenever they are the more electronegative atom in the structure, the halogens are monovalent. Now the actual shape we're saying is going to be triangular bipyramidal. Take just a quick glance at that in case you've forgotten. Five bonded atoms around the central phosphorus atom. So how do we understand this in valence bond theory? Electron configuration is 3s2, 3px1, 3py1, 3pz1 for phosphorus. Here it is. Now it can form 3 bonds the way it's situated, but we need 5. So the proposition is that phosphorus will mix together its 3s, all of its p's, and 1 of its d orbitals to form 5 hybridized orbitals. Promoting 1 electron produces 5 half-filled orbitals. It turns out that the dz squared orbital has the best shape and is the one that's used to form these hybrid orbitals. So this will give us 5 sp3d hybridized orbitals. Since we mix together 1s, 3 p's, and 1 d, they are called sp3d. 1 plus 3 plus 1 makes 5. Each of them are half-filled. Each of them can now overlap with a half-filled pz orbital of a halogen, such as chlorine, giving us 5 covalent bonds, and they'll be arranged, as you see here, in a triangular bipyramidal structure. Now, the bonds are, in fact, polar covalent because chlorine has electronegativity of 3, phosphorus is 2.1, the difference is 0.9, so it's polar covalent, but the dipoles will cancel both in the equatorial plane and in the axial plane. So on the whole, PCl5 is a non-polar molecule. Its molecular geometry and its electronic geometry are both triangular bipyramidal. I mentioned the dz squared orbital is preferentially hybridized, and it's due to its shape. It seems to accommodate the shape of the structure best to separate the 5 electron clouds as far as they can. Let's just remind ourselves of what the shape of the dz squared orbital is. It's this one right here, and it looks a lot like a p orbital in its shape. So PCl5 has triangular bipyramidal molecular and electronic geometry. The PCl bonds are polar, but the dipoles cancel. The molecule is nonpolar. Page 138, compounds of the type AB4U. Sulfur tetrafluoride is an example. Let's start by drawing the structure of sulfur tetrafluoride, or sulfur 4-fluoride. Sulfur is in group 6A, so it's going to have 6 valence electrons. That's something of a Lewis structure for the molecule, but what's the actual shape? We notice there's 5 clouds of electrons. It's going to be triangular bipyramidal. How can we draw that? So the fluorines will occupy axial positions and then the equatorial positions, and one of the equatorial positions will be the non-bonded pair of electrons. What shape is that? Well, the electronic geometry is in fact triangular bipyramidal. What would you call the molecular geometry? Well, there is a name for that. It's called seesaw. So can you picture this? A seesaw is a teeter-totter. I know a seesaw is a pretty technical name, but that's what it's actually called. So we have these 4 groups, and the non-bonded pair of electrons makes the shape of a teeter-totter or seesaw. So sulfur, 3s2, 3px2, 3py1, 3pz1, needs to form 5 bonds. So sulfur will mix together its s orbital, all of its p orbitals, and its 3dz squared orbital to come up with 5 new orbitals. Promoting 1 electron produces 4 half-filled orbitals. Hybridized orbitals, identical in energy, they're degenerate. sp3d, 4 of them are half-filled and overlap with fluorine to form 4 sigma bonds. The unshared pair of electrons is a lone pair that doesn't bond. The non-shared pair of electrons is in the equatorial plane. Because there's more room in the equatorial plane, there's a larger bond angle, and they take up more space. And if you can somehow picture this on your side, these are the legs of a teeter-totter, and this is the part where people sit on this teeter-totter. That's called a seesaw. SF4 has triangular bipyramidal electronic geometry, but its molecular geometry is seesaw. The SF bonds are polar. Delta En is 1.5, but dipoles largely cancel, so the molecule is low melting, a nonpolar liquid. Let's look at compounds of the type AB3U2. 1 central atom, 3 bonded atoms, 2 unshared pairs of electrons. We'll consider the case ClF3. Let's start by drawing the structure of ClF3. So chlorine is the central atom. It's less electronegative. It's in group 7A. It has 7 valence electrons. 3 of them will be bonded to fluorine. That leaves 2 non-bonded pairs of electrons. So there's 5 electron clouds around chlorine repelling each other. What would that actually look like in 3-dimensional space? Now the fluorines will occupy the axial positions where there's less space. I'll put one back here as well. And then the 2 non-bonded pairs would occupy the equatorial positions where there's more space. So the electronic geometry of this is again triangular bipyramidal. I don't want to write it out. What's the molecular geometry? What does that look like? Can you see the letter T there among the atoms? The molecular geometry is T-shaped. Alright, let's take a look over here. Here's the electron configuration of chlorine, group 7A, 3s2, 3px2, 3py2, 3pz1. It can form one bond if it's unhybridized, but if it's going to form three bonds, it has to hybridize. So let's say that chlorine hybridizes its s, all of its p's, and the 3dz squared orbital to form 5 identical orbitals. Promoting one electron will produce 3 half-filled orbitals. Sp3d hybrid orbitals. 2 of them are filled, 3 of them are half-filled. Those that are half-filled can form 3 sigma bonds with fluorines. Here's the triangular bipyramidal structure in which the non-bonded pairs are in the equatorial positions. There will be some dipoles here. Chlorine has electronegativity of 3, fluorine is 4. The difference is pretty significant, 1.0 difference. But looks like it's going to more or less cancel. We expect this molecule to have low polarity. The electronic geometry is, of course, triangular bipyramidal, but the molecular geometry is described as being T-shaped. So it does kind of make the letter T, right? It turns out that CF3 is a non-polar gas that with a low boiling point. Page 139, please. Page 139, compounds of the type AB2U3, central atom, 2 bonded atoms, 3 unshared pairs of electrons. We'll consider the example of xenon difluoride. Xenon's a noble gas. Do they form compounds? Well, not very many, but some of the lower noble gases beginning at krypton and down have been encouraged to form compounds with fluorine. They're not very stable, but nonetheless they're real. So let's consider them. As we want to draw the structure, we always look up electronegativity, and of course none has ever been assigned to the noble gases. So what do? Well, it turns out that all noble gas compounds are in fact covalent compounds. They're not ionic. And the noble gas is known to be the central atom. So you need to bear that in mind. Always draw the noble gas as the central atom in a structure. So xenon is in group 8A, so it should have 8 valence electrons. That's the Lewis structure of xenon difluoride. What would the shape be? Well, how many clouds of electrons are around xenon? There's 5, right? 5 electron pairs. How can we draw that? 5 electron clouds means it's going to be triangular bipyramidal. And the axial positions will be occupied by the smaller groups, the equatorial positions by the non-bonded pairs of electrons. So what's the molecular geometry then? It would be linear, wouldn't it? Let's take a look. Let's go through the process. Xenon is element 54. It has this electron configuration, 5s2, 4d10, and a full valence shell 5p6. To explain the shape, we need 5 hybridized orbitals. So we believe that xenon would hybridize its 5s. The 4d is full, so we can't use that. 3 5p's, and the next available d orbital. So all in the valence shell. Promoting one electron produces 2 half-filled orbitals. That'll give rise to 5 hybridized orbitals. We'll call them sp3d because they're made from 1s, 3 p's, and a d. 3 of them already contain non-bonded pairs of electrons. 2 of them are half-filled and can overlap with a fluorine to form xenon difluoride. Here's the structure. Again, non-bonded pairs of electrons in the equatorial plane, and the fluorines on the axial plane. And so you can see that the molecular geometry is in fact linear. Xenon difluoride has triangular bipyramidal electronic geometry, but its molecular geometry is linear. The dipoles, whatever there is there, we can't tell, they will cancel and the molecule is nonpolar. It's an unstable compound. So to summarize, for 5 electron clouds we have these arrangements. And I borrowed this beautiful image from P Interest. We could have the type AB5, like we see here, with 5 bonded pairs and no lone pairs, as for example we saw in PCl5. AB4U, for example SF4, has triangular bipyramidal electronic geometry, but a seesaw molecular geometry. AB3U2 has 2 non-bonded pairs of electrons and 3 bonded pairs, like in ClF3. Here we see it here. The molecular geometry is said to be T-shaped. And finally we have AB2U3, as in xenon difluoride, whose molecular geometry is linear. Page 140. Page 140. This brings us to our last group of compounds, those with 6 pairs of electrons, and they have octahedral electronic geometry. That would include AB6, AB5U, and AB4U2. So recall that in octahedral structures there are no equatorial or axial positions. All the positions have equal space. In octahedral compounds, it's the dz squared and the dx squared minus y squared orbitals that are hybridized, along with s, px, py, pz orbitals. Let's take a glance at the shapes of those d orbitals. So the dx squared minus y squared has electron density right along the xy axis, and the dz squared orbital has electron density on the z-axis largely, and also in the xy plane. So as you look at these two, it's not difficult to envision that they do in fact have electron density that lies along the xy axis and z axis of an octahedral structure. Alright, let's start. We're asked to draw the structure of a compound of the form AB6, and our example is SF6. So here's SF6. Sulfur is in group 6A. But what's the shape? Sulfur, 3s2, 3px2, 3py1, 3pz1. It needs 6 half-filled orbitals, so the model says it will hybridize the 3s, all of the 3p's, and the first 2 available 3d orbitals. And it turns out that the dz squared and dx squared minus y squared have the shapes that best fit the octahedral structure. Promoting 2 electrons produces 6 half-filled orbitals. They can then overlap with half-filled 2pz orbitals of 6 fluorines. Here's the shape. All positions are equivalent. It's octahedral in both its molecular and electronic geometry. There would be significant dipoles. 4.0 minus 2.5 is 1.5, but they'll cancel in every direction. So as a whole, SF6 should be nonpolar. It is in fact a gas, and it's insoluble in water. Let's look next at a compound of the type AB5U. We'll consider BRF5. Let's draw the structure of that. Bromine is in group 7. Remember, the single unpaired electrons always bond. The pairs may or may not. What's that going to look like? We still have 6 electron cloud. So what's the molecular geometry of that? Ignoring the non-bonded pair, what's that look like to you? Alright, we'll come back to that. So here's bromine, 4s2, 4px2, 4py2, 4pz1. We want 6 identical orbitals in terms of their shape and their energy. So we're going to suggest that bromine hybridizes as 4s, all of its 4p's, and 2 of its 4d, namely 4dz squared, 4dx squared minus y squared, and now it has 6 hybridized orbitals. Promoting 2 electrons will produce 5 half-filled orbitals. 5 of them are half-filled, 1 is full, so the full orbital is not involved in bonding. The other 5 do form bonds. Here's the shape. One of these is a non-bonded pair of electrons. Here it is. All right, what's left over? What would you call this shape? If you filled it in, it's called a square pyramid. The molecular geometry is square pyramidal. I don't think I can draw that. Nope. Okay. BRF5 has octahedral electronic geometry, but its molecular geometry is square pyramidal. The bromine to fluorine bond is pretty polar, 1.2, but the dipoles should largely cancel, and in fact the molecule is nonpolar. Page 141, please. Page 141, the last type of compound that we can draw with 6 electron clouds, A, B4, U2. An example would be Xenon Tetrafluoride. Let's start by drawing its structure. Xenon is in group 8A. It's a noble gas. Don't leave any unpaired electrons, right? Unpaired electrons don't remain in bonded structures. They're too unstable. You'll learn more about that later. What's the structure of that going to be? Well, there's 6 electron clouds, so again it will be octahedral. It doesn't matter where you put the first non-bonded pair of electrons. Let's say I put them on top. But once you've put the first pair, you have to remember to put the second pair on the opposite side. Why is that? Non-bonded pairs of electrons take more space. They need to spread out. So always put the non-bonded pairs of electrons opposite each other. So what is the shape of the molecular geometry here? Let's look at the structure. 5s2, 5px2, 5py2, 5pz2, full valence shell. We need 6 hybridized orbitals for 6 pairs of electrons. We believe that xenon will hybridize its 5s2, all of its p's, and 2 of its d's to give a grand total of 6 hybridized orbitals. Here they are. Promoting 2 electrons produces 4 half-filled orbitals. Sp2 orbitals times 6. 2 of them are filled, 4 of them are half-filled. Those that are half-filled can overlap with fluorine atoms to form SF4. Here's the structure. These dipoles will certainly cancel, and so the molecular geometry is said to be square planar. I believe I have an animation of it here we can look at. It definitely looks square planar. Interesting animation. So in summary, covalent compounds with 6 regions of electron density are sp3d2 hybridized and adopt the molecular and electronic geometries shown in the following table. And there's a great image here, complements of p interest. AB6, like SF6, have 6 bonded pairs of electrons. The molecular geometry is octahedral. AB5U have 5 bonded pairs and 1 unshared pair. Molecular geometry is square pyramidal. AB4U2, like xenon tetrafluoride, Electronic geometry, as in all cases, is octahedral, but the molecular geometry will be square planar. On page 142, here's that VSEPR summary, again from P interest. 2 electron clouds is linear, 3 electron clouds, triangular planar, 4 electron clouds, tetrahedral, 5 electron clouds, triangular bipyramidal, and 6 electron clouds, octahedral, and then we have variations involving unshared pairs of electrons for tetrahedral, triangular bipyramidal, and octahedral. Page 144. So far we've only considered compounds containing single bonds. Valence bond theory would not be much of a theory if it didn't account for molecules containing multiple bonds. So compounds containing double and triple bonds. Atoms forming a double bond share 2 pairs of electrons in the same region of space. Here's carbon dioxide. 2 pairs of electrons are shared in the same region of space on the right side and again on the left side. Likewise, in ethylene, these carbons share 2 pairs of electrons in the same region of space. Atoms forming triple bonds share 3 pairs of electrons in the same region of space. In the case of hydrogen cyanide, here's 3 pairs of electrons in the same region of space, as is true in acetylene. So the formation of double and triple bonds require their own type of hybridization of atomic orbitals. It's a small modification. The atoms which most commonly form double bonds are carbon, nitrogen, oxygen, sulfur, and phosphorus, and occasionally halogens. And the atoms which, it says commonly but actually exclusively, form triple bonds are carbon and nitrogen. A double bond is made of 1 sigma bond and 1 pi bond. This diagram doesn't show which is which. A double bond is made of a sigma bond and a pi bond. A triple bond is made of 1 sigma bond and 2 pi bonds. 1 sigma bond and 2 pi bonds. And you'll appreciate the difference on the next page. Page 145. Page 145. Bonding in carbon compounds. This may take some time for you to grasp. I'll do my best to help you visualize it. So carbon is extremely versatile. It can form 4 single bonds, as you see in ethane here. It can form a double bond and 2 single bonds. It can also form a triple bond and a single bond, even form 2 double bonds. How does it do all this? In all cases, carbon needs to hybridize because electrons have to be redistributed. Carbon will need 4 bonds in every case, so it's always going to be hybridized. But the hybridization is different depending on the type of compound that's going to be formed. When carbon forms 4 single or sigma bonds, it's Sp3 hybridized, as we already discussed. Here are the 4 Sp3 hybridized orbitals, 110 degrees apart. Here I've stood them up like bowling pins, showing you they're half-filled orbitals, and the overlap as we discussed. But what happens when it wants to form a double bond here? So this is different. Carbon still needs 4 bonds. It still needs 4 half-filled orbitals, but it only reshapes or hybridizes 3 of them. So picture carbon mixing together an s and only 2 of the p orbitals, leaving the pz orbital unhybridized. Now it's going to have an electron in it. It's going to form a bond, but it's not concluded in the reshaping. So s and 2 p's are mixed together to give us 3 sp2 hybrid orbitals with 1 unhybridized p orbital. You need to remember that any pi bond is made from an unhybridized orbital. So what's the shape of sp2 hybridization? What shape would that be? I'm showing you here it's 120 degrees flat triangle. Do you recall we looked previously at BH2? We said that was Sp2 hybridized. It's triangular planar with 120 degree bond angles. Well, that's going to be the shape of carbon with its 3 sigma bonds. 120 degrees apart, flat triangle. But the unhybridized 2pz orbital remains as a p orbital above and below the plane of that, like so. And that's going to form the pi bond. So here we have ethylene. So carbon is going to form 3 sigma bonds, one with an adjacent carbon, 2 with hydrogen. That's the triangular planar bit. And then it'll have the unhybridized pz orbital sitting above and below the plane of the sigma bond between the 2 carbons. You see, you can't put 4 pairs of electrons in the same space. They repel. So to get that second bond in there, carbon links up with another carbon, which is also Sp2 hybridized, and their p orbitals overlap above and below the sigma bond. So the sigma bond lies directly between the 2 carbon nuclei, and it's a strong bond. But the pi bond can't fit directly between the nuclei, so it's slightly above and below. It's going to be a weaker bond. And you'll see in organic chemistry upcoming in the fall semester that pi bonds, carbon-to-carbon pi bonds, are sites of reactivity. These are reactive sites because the bonds are not that strong and they can be attacked. So here we have 2 carbon atoms, each Sp2 hybridized, each bonded to 2 hydrogens and the other carbon, and the pi bond is made from the unhybridized pz orbital above and below the plane of the sigma bond overlapping. Now I realize there are 3 lines here showing. There's 2 electrons in the sigma bond, and you can think of there being 1 electron in each of the lobes of the pi bond. So there's only 2 bonds here, the sigma and the pi. Here's a picture. Carbon bonding to another carbon in C2H4 ethylene. Carbon has 3 sigma bonds and 1 pi bond made by the overlap of the unhybridized pz orbital with another unhybridized pz orbital. The total of 4 electrons in here. 2 in the sigma bond and then 2 that are spread out above and below the plane of the sigma bond. Here's another view of it, showing how these orbitals overlap. So these 2 lobes are actually 1 pi bond. The carbon can also form a triple bond, as for example in acetylene. A carbon-to-carbon triple bond still has 4 bonds. It'll have 2 sigma bonds and 2 pi bonds. Remember, a triple bond is made of 1 sigma bond and 2 pi bonds. So in this triple bond, there's 2 pi bonds and 1 sigma bond. How does it do that? We still need 4 half-filled orbitals, so electrons will promote, but only 2 of those orbitals will mix together. Will mix together an S and a P and form 2 sp hybridized orbitals, leaving 2 unhybridized p orbitals. One will be pz and one will be py. Do you recall what an sp hybridized structure looks like? Like beryllium hydride. It's a linear molecule. So carbon does that. It's going to have 2 sp hybridized orbitals that are linear. Here's one of the sp hybridized orbitals and here's the other one. One will be bonded to hydrogen, the other will be bonded to the other carbon. And then we have this unhybridized pz orbital that sits above and below the plane of the sigma bond. And then we have a second unhybridized orbital. Let's say this is the py orbital sitting to the side of the plane of the sigma bond. Let's try and visualize it here. Here are my 2 sp hybridized orbitals to hydrogen and carbon. Here is the unhybridized pz orbital, which overlaps above and below the plane of the sigma bond to another unhybridized pz orbital from another carbon. That gives me one pi bond. The second pi bond is made from another unhybridized p orbital. Let's say this is the py orbital, and it overlaps side to side with another unhybridized py orbital from another carbon. So there we have three bonds. There are two electrons in the sigma bond, and then there's one electron, let's say here and here, and then one electron here and here. Now the electrons are moving at 1/10 the speed of light. We can't say where they are at any given time, but you need to appreciate there's a total of 6 bonded electrons. 2 are in the sigma bonds, and then 2 each in the pi bonds. Let's take a look at an image of this. So here's an image representing the orbitals in sp hybridized carbon. There's a carbon here and here. And we'll consider the carbon on the left sigma bonded to a hydrogen, and then sigma bonded to a carbon. That's sp2 hybridized. It's linear. But then there are 2 unhybridized orbitals on carbon. There's this 2pz orbital that sits above and below the plane of the sigma bond, overlapping here with another unhybridized 2pz orbital from another carbon. Then we have the other unhybridized 2p orbital overlapping with an unhybridized 2p orbital, and this one sits not above and below, but rather in front and behind the plane. So here we actually have 6 electrons in the same region of space between 2 carbons. So it's counted as a single region of electron density, a triple bond. Take a look at page 146. This is the bonding arrangements or hybridization arrangements with nitrogen. We've already pointed out that nitrogen already has an electron configuration suitable for forming 3 bonds, 3 half-filled p orbitals, but not suitable for forming the shapes of the nitrogen molecules. And so we do still propose hybridization that mixes together the s orbital and 3 p's to give us, as we saw previously, sp3 hybridized nitrogen. In ammonia, nitrogen has 3 sigma bonds and 1 unshared electron pair, and they're all in sp3 hybridized orbitals. Now, ammonia is a base. It can react with H+ to form ammonium ion, and now we have 4 sigma bonds, still sp3 hybridized. We've looked at this one before. Let's move on and look at sp2 hybridization of nitrogen. So like carbon, to form a pi bond, it needs to leave one of its orbitals unhybridized. Let's just say that's the pz orbital for sake of argument. I'll color it for recognition. This one will not be hybridized. It's still half-filled. It can still form a bond. So nitrogen hybridizes the s and the 2 of the p orbitals to give an sp2 hybridized atom. Recall that sp2 hybridized atoms have a triangular planar structure. So here's nitrogen. It's 3 hybridized orbitals, 120-degree bond angles, triangular planar, and the unhybridized pz orbital above and below the plane. So in the case of this compound, N2F2 dinitrogen difluoride, the nitrogen bond is a double bond made of 1 sigma and 1 pi bond. So I've drawn it here. So we'll look at this nitrogen on the front. Here are its 3 hybridized orbitals containing a nitrogen to fluorine sigma bond, a non-bonded pair of electrons, and then nitrogen to nitrogen sigma bond. But the unhybridized pz orbital, which I've colored blue here, will overlap above and below the plane of the sigma bond here, and so this is the pi bond. So we see 3 lines, if you will, 2 blues and 1 yellow, but that represents 2 pairs of electrons, a total of 4 electrons. There are 2 electrons in the sigma bond, and there are then 2 electrons in the blue overlapping pi bond. Nitrogen is the only other element besides carbon that can form stable triple bonds. And so like carbon, in order to do that, it will only hybridize the s and one of its p orbitals, and it will leave two of its p orbitals unhybridized. So let's say, for example, that this is the py orbital, which is unhybridized. I'm just coloring for identification purposes. And there's the pz orbital. So if nitrogen is sp hybridized, recall that sp hybridized atoms are in fact linear. So it'll have one non-bonded pair of electrons and then one sigma bond, and that's linear. Then we'll have two unhybridized orbitals. There'll be a pz orbital above and below the plane, and the py orbital side to side. So now it can form a triple bond. In this compound, nitrogen is triply bonded to carbon in acetonitrile. Here's the sp hybrid orbitals, non-bonded pair of electrons, and sigma bond to the carbon. Then we have the p orbital, which is overlapping above and below the plane of the sigma bond to form one of the pi bonds. And then we have the other p orbital, the unhybridized py orbital, overlapping side to side to give us that triple bond. So looks kind of confusing there, but there are in fact a total of 6 electrons in this triple bond. There are 2 in the sigma bond, and then another 2 in the unhybridized pz orbital, and another 2 in the unhybridized py orbital. Here's an image from the web showing here is the nitrogen molecule, N2. It has a non-bonded pair of electrons in an sp hybridized orbital, and then there's an overlap here, sp to sp. Then we have the pz orbital, and here's the py orbitals overlapping side to side. Clever atoms, aren't they? Look next at page 147. Let's look at oxygen. The ground state electron configuration of oxygen, S2, px2, py1, pz1. It can form 2 bonds the way it is, but this does not produce the observed tetrahedral geometry. So it does hybridize the s and all 3 p orbitals to form sp3 hybridized oxygen, which we commonly see in, for example, water. Water has 2 sigma bonds and 2 pi bonds, but they're all in sp3 hybridized orbitals. You know that water can react with hydrogen ion to form hydronium ion, and now we have sp3 hybridized oxygen with 3 sigma bonds and 1 non-bonded pair. Oxygen can form and does form double bonds, and that requires sp2 hybridization. So that's the same as we saw with nitrogen and carbon. In order to form this pi bond, one of the 2 pz orbitals, I'll color it blue, must remain unhybridized to form the pi bond. So here's oxygen. Oxygen is sp2 hybridized. That means it has 3 electron clouds that are 120 degrees apart. 2 of them happen to be non-bonded electron pairs. One of them is a sigma bond. Here's oxygen in the compound acetone bonding with carbon, which is also sp2 hybridized. Here's the overlap of the pz orbital. So here's the sigma and the pi bond in oxygen. And there are its sp2 hybrid orbitals. And here's an image of carbon dioxide in which the carbon is sp hybridized to form 2 pi bonds, but each oxygen is only sp2 hybridized to form 1 pi bond. That's sp2, sp2, and sp hybridized. Page 150. What about halogens? We've already discussed them, but I'd like to make sure you have it down pat. When they form only one single bond, there's no need for them to reshape their orbitals or promote electrons. They do not need to rehybridize. So look at the electron configuration of chlorine or fluorine or any halogen, S2, px2, py2, pz1, one orbital ready to share. And since it's only forming a single bond, there's no real reason for it to rehybridize. So in a formula such as this, we would say that chlorine is simply unhybridized. What about hydrogen? We mentioned at the beginning of the chapter that hydrogen already has a half-filled 1s orbital that's appropriately shaped for bonding.
So there's no reason to propose its hybridization.
Let's consider silicon. So like carbon, it is a group 4a element with 4 valence electrons. As expected, silicon forms Sp2 hybridized tetrahedral compounds with 4 substituents. Simple examples include silicon tetrabromide. Silicon forms a few compounds in which it has double bonds. However, silicon's large size makes p orbital overlap for pi bonds less effective than in carbon compounds. Unlike second period elements, which cannot accommodate more than 8 electrons in the valence shell, silicon is a third period element and it can expand its valence shell to accommodate 10 electrons when it's sp3d hybridized, that is 5 substituents like in SiF5-, and even up to 12 electrons when it's sp3d2 hybridized with 6 substituents as in SiF6-2. Let's consider this last case. So fluorosalicic acid, H2SiF6, it forms when silicon tetrafluoride reacts with hydrofluoric acid. This has been added to drinking water as a source of fluoridation to prevent tooth decay. So here's silicon tetrafluoride in hydrofluoric acid making fluorosalicic acid. Now fluorosalicic acid is diprotic and can be deprotonated with 2 moles of NaOH, producing this hexafluorosilicate ion, SiF6-2. Let's see if our valence bond theory allows us to predict its structure correctly. We'll start by drawing a Lewis structure for SiF6-2. So silicon is in group 4a, so it has 4 valence electrons. We can combine 4 fluorines and make 4 covalent bonds. That's SiF4, but how do we get SiF6-2? To get 2 negative charges, it must combine with 2 fluorides. And each of these fluorides is an electron pair donor. And that'll give us a structure of SiF6. Now with 6 electron clouds, with 6 ligands, that should be octahedral. The total charge on this is -2. So the formal charge on silicon has to be -2 since it has 6 electrons that it owns in the valence shell. All right, let's look at our formal representation here. Group 4a will have the electron configuration 3s2, 3px1, 3py1. In order to form 6 bonds, 6 sigma bonds, it'll need 6 hybridized orbitals. So we're saying the hybridization is sp3, and we need 2d orbitals, so it's sp3d2. Notice we promote 1 electron. We still need 2 of these empty orbitals to accommodate the pairs of electrons that come from the 2 fluorides. That's sp3d2 hybridization. Notice we have 4 covalent bonds formed by sharing 1 electron from silicon with fluorine, but then we have this pair of electrons that are being donated by 2 fluorides, and that gives us 6 sigma bonds. Octahedral. So the model can be extended. Page 151. Let's take a look at phosphorus. Phosphorus, like nitrogen, is a group 5a element, so it has 5 valence electrons. As expected, phosphorus forms sp3 hybridized compounds with 3 substituents, just like nitrogen, just like ammonia. Simple examples include phosphorus tribromide. Phosphorus forms some compounds in which it has double bonds to oxygen, for example, phosphoric acid. However, phosphorus's large size makes p orbital overlap for pi bonds less effective than in carbon compounds. Like some other third period elements, phosphorus can be bonded to 4 or 5 or 6 atoms. I have some examples here. Problem: draw a Lewis structure of phosphoric acid. Draw an electron configuration diagram for phosphorus showing its hybridization in this compound. Name the type of hybridization. Let's start by drawing the structure of phosphoric acid. I'm going to do this very quickly. We've done it several times already. It's a triprotic acid. Acidic hydrogens are bonded to oxygen. There's 3 of them. There are 4 oxygens. Give oxygen 6 electrons that it owns, 8 in the valence shell, and we're good. So that's the structure of phosphoric acid. How many bonds does it have around the phosphorus? Okay, it's got 1, 2, 3, 4, 5. So it needs 5 orbitals, but this bond is a double bond. And a double bond, remember, is made of 1 sigma and 1 pi bond. And don't forget, pi bonds are always made from unhybridized orbitals. So you will not need a hybridized orbital for one of these 5 bonds. You'll just need 4 hybridized orbitals, again because pi bonds are always made from unhybridized orbitals. So we need sp3 hybridization, right? 4 hybridized orbitals for phosphorus. This one's tricky, but I've warned you of it. So here's electron configuration of a p5 element, s2, px1, py1, pz1. We said we needed 4 hybridized orbitals, but also we need to form a 5th bond, which is an unhybridized orbital. So phosphorus promotes 1 electron from the 3s orbital into the 3dz² orbital, giving 5 half-filled orbitals. 4 of them are sp3 hybridized and overlap, and then the 5th one is unhybridized, and that is a d orbital that overlaps with a unhybridized p orbital of oxygen to give the pi bond. That one's a bit tricksy, right? So the hybridization, as you can see, is sp3 hybridized, not sp3d. So the 3dz² remains unhybridized to form the pi bond. The molecular geometry is tetrahedral, and as is the molecular geometry for phosphorus. And what about sulfur? Sulfur, like oxygen, is a group 6A element. It has 6 valence electrons. So as expected, it forms sp3 hybridized compounds with 2 substituents, just like oxygen does in water. Simple examples include dimethyl sulfide. Well, so would be hydrogen sulfide, would be another even simpler example. H2S would be an example. Sulfur can form bonds to 3, 4, 5, and even 6 atoms, SF6 we've looked at previously. Draw a Lewis structure for sulfur oxytetrafluoride, SOF4. Draw an electron configuration diagram for sulfur showing its hybridization in this compound. Name the type of hybridization. We're going to start by drawing the Lewis structure of SOF4. Sulfur is in group 6A, just like oxygen. SOF4. What are the electronegativity values? 2.5 for sulfur is the same as that of carbon. 3.5 for oxygen, 4.0 for fluorine. Sulfur is least electronegative, and so it's a central atom, plus it has the ability to have an expanded valence shell because it's a third period element. I want to ask you, what will be the shape of this molecule? To answer that, you count up the number of electron clouds. There are 5. So 5 electron clouds means it'll be a triangular pyramid shape. Sulfur is in the middle. We have 1 double bond, so that would require a little more space. That would be on the equatorial plane, and the remainder are fluorines. So that's triangular bipyramidal in shape. So regarding its hybridization, how many bonds are here? 6 bonds, so it needs 6 half-filled orbitals, but be careful and recall that in the double bond, one is sigma and one is pi. And the pi bond does not involve a hybridized orbital. So we need 6 half-filled orbitals, but only 5 of them are hybridized. Let's take a look at that. Here's the ground state electron configuration of a 6A element, S2, Px2, Py1, Pz1. Recall we need 6 bonds, 6 half-filled orbitals, so 2 electrons are promoted to give us a total of 6, but only 5 of them are hybridized. We need the unhybridized d orbital to form the pi bond. Therefore, it will be sp3 dehybridized. Here it is, sp3 dehybridized. The 5 hybridized orbitals overlap, forming sigma bonds, and then the unhybridized d orbital overlaps with an unhybridized p orbital from oxygen, forming the pi bond. And there's a structure. SOF4 is triangular bipyramidal. So as it turns out, our valence bond model is fairly versatile. It can explain the bonding in a variety of covalent compounds. Page 152. Let's see if we can summarize what we saw in this chapter. So this is a summarization of hybridization types. I collected a variety of formulas, and looking at the formula we should be able to figure out the hybridization state of any atom in it. So this column here, atom column, I'm saying the atom I'm referring to in a particular compound. So let's start right here. Let's say boron in BF3. How many pairs of sigma electrons are there? In other words, how many sigma bonds are there? You may need to draw the structure, but I'm hoping by this time you can tell just by looking at it. There'll be 3 sigma bonds. How many pi bonds? None. How many non-bonded pairs of electrons? None. How do I know that? Because boron's in group 3A and it has 3 dots, and you can easily figure this out. And the compound type is AB3, and the shape is triangular planar. So what's the hybridization state? If you have 3 sigma bonds, it requires 3 hybridized orbitals, which would be sp2. Okay, look at the carbon, either one, in ethene. How many sigma bonds are involved in each carbon? Can you see there'd be 3, 2 to the hydrogens, and 1 in the double bond. There's 3 sigma bonds. How many pi bonds? Well, each carbon has 1 pi bond. How many non-bonded pairs of electrons? None. What's the hybridization state of carbon? It has to be sp2. Why? Because it needs 3 hybridized orbitals for the sigma bonds. Remember that pi bonds do not involve hybridized orbitals. Non-bonded electrons do, but there are none in this compound, so it's sp2 hybridized. How about the oxygen in O2? Each oxygen has 1 sigma bond. It has 1 pi bond, but pi bonds are not involved in hybridization. And then each oxygen would have 2 non-bonded pairs of electrons, and they do require hybridized orbitals. There are a total of 3 pairs of electrons that require hybridized orbitals, and therefore it is sp2 hybridized. And so on down the chart. If you find it useful, great, and if you don't, then just move on. Page 153. Here's an exercise where I'm asking you to fill in this table with respect to the central atom in each compound. And I won't take this up. We've done many examples, but the answers are on the next page in your notes. At the bottom of the page, something that I think is fairly important. With some practice, hopefully by this stage of the game, you can identify the hybridization state of an atom by just looking at it in its structure. So for example, what's the hybridization state of hydrogen in ethanol? I hope you're going to say unhybridized. Remember, hydrogen does not need to hybridize any orbitals to have a single bond, so it's always unhybridized. What about this oxygen? What's its hybridization state? Well, it's got 2 sigma bonds. and 2 non-bonded pairs, and all of those require hybridized orbitals. We need 4 hybridized orbitals, which would be sp3 hybridized. Take a look at alanine. What's the hybridization state of the nitrogen in this compound? Well, the nitrogen has 3 sigma bonds and 1 non-bonded pair of electrons, all of which require hybridized orbitals. There are 4 in requirement. That's sp3 hybridized. What about this carbon here? Hybridization state. Count up the number of non-bonded electrons, none. The number of sigma bonds, 1, 2, 3. Pi bonds don't matter. They do not involve hybridized orbitals. Therefore, 3 hybridized orbitals for 3 sigma bonds makes this sp2 hybridized carbon. What about this oxygen? Hybridization state. Well, count up the number of non-bonded electron pairs and the number of sigma bonds, because those require hybridized orbitals. Ignore the pi bond. There are 3 pairs of electrons that require hybridized orbitals. That's sp2 hybridized. Try 2-butene nitrile. What about this nitrogen? What's its hybridization state? Well, how many sigma bonds? You say 1, you're right. How many non-bonded pairs? 1. A total of 2 pairs of electrons that need hybridized orbitals. That would be sp hybridized. What about the carbon? It's got 2 sigma bonds and 2 pi bonds. Ignore the pi bonds. 2 sigma bonds requires sp hybridization. What about this carbon? How many sigma bonds? 1, 2, 3. Non-bonded electrons? None. So it just needs 3 hybridized orbitals. That would be sp2 hybridized. You got the idea? Well, let's do one more here. How about sulfur? Count up the number of non-bonded electrons. None. Number of sigma bonds. 1, 2, 3, 4. There's a sigma bond in every double bond. Ignore the pi bonds. So we have a total of 4 electron pairs that are sigma bonds that require hybridized orbitals. This is an sp3 hybridized sulfur. How about this sulfur? How many sigma bonds? 2. How many non-bonded pairs? 2. All of these require hybridized orbitals. We have 4 pairs of electrons requiring hybridized orbitals, sp3 hybridized. The answers for this page are also on the next page. And finally, page 154. Page 154, I've drawn the structures of a number of second period and third period elements, and in each case I've given some structures that show that element in various hybridization states. For example, look at nitrogen in this compound. This would be nitrous acid. What's the hybridization state of nitrogen in this compound? The answer is, how many pairs of electrons does it have that require hybridized orbitals? Well, sigma bonds and non-bonded electrons. So there's 1 here, there's a non-bonded pair here, and there's 1 sigma bond in the double bond. There are 3 pairs of electrons that require hybridized orbitals. It is sp2 hybridized, as it says here in the leftmost column. Let's try one more. How about under sulfur? How about this compound right here? What is that? That's sulfur dioxide. How many pairs of electrons does it have that require hybridized orbitals? Again, not the pi bonds. Sigma bonds and non-bonded pairs of electrons require hybridized orbitals. It has 1 sigma bond here, 1 here, and 1 non-bonded pair. There are 3 pairs of electrons that require hybridized orbitals. This also is sp2 hybridized in the sulfur. That's how you read the table, so you should go through it and test yourself to see if you understand it. And that's it for our chapter on VSEPR and valence bond theory. Keep in mind that valence bond theory is a model. It works well for certain types of compounds, covalent compounds. For transition metals, there's a different model, crystal field theory, for example. And so the models continue. We have yet to find a single and simple unified model that would describe all types of compounds. And so we're stuck with a collection of models that work for various types of compounds. And we piece them together as best we can. And that'll be it for this chapter on valence bond theory and VSEPR.